sine omega t plus delta. This delta, the value of that delta will tell you where exactly the object is when you start the clock. If delta equal to 0, the object is at the origin and is beginning to move up. If delta is pi by 2, when you start the clock, the object is at the upper extreme and is beginning to come down. If this delta is pi, it means the object has actually gone up and come back to the origin and is now beginning to move down. If this delta is 3 pi by 2, it means the object has gone up, come back to the origin, and has now gone all the way down. It is at the lower extreme. And delta can have any intermediate value. When the oscillating object is here, delta has a value. So what does the value of delta really tell you about the state of oscillation? It tells you where exactly is the object when you start your clock. There you are. This is the oscillation, and when you start the clock, when the object is at the origin, the displacement will be a sine function. You can see it traces out that sine graph. So the displacement for vertical oscillations, you see, normally when you measure distances in a vertical direction, we call it y. What do you call if distances are measured in the horizontal direction? We call it x, don't we? So the displacement for vertical oscillation is y equal to a sine omega t plus delta. You see, an oscillation can also be horizontal. Have you seen a horizontal oscillation? Well, let me see if I can show you a horizontal oscillation. Now look at this oscillation. You can see a spring. When you pull on the spring, you go to the right extreme from the equilibrium position, and if you leave it, the mass will oscillate between a left extreme and a right extreme. Now displacement in this case will be measured as x equal to a sine omega t plus delta. So you can have a horizontal oscillation or vertical oscillation. Depending on the displacement is vertical or horizontal, we will use x or y to represent that. Okay. So what will be the equation for that oscillation? For a horizontal oscillation, x equal to a sine omega t plus delta. All right. Let's now write the equations for position, velocity, and acceleration of an oscillation. When we have an equation for the displacement, that is actually the position function, because the displacement tells you where exactly is the position of the oscillating object. So we already know the position function. The position function for such an oscillation is y of t, y as a function of time, is a sine omega t plus delta. That represents the displacement, but that is the same as the position function. Now, you know from your discussion on Physics 1, the derivative of the position function will be the velocity function. If this is the position function, can you find the derivative of this? And give me an expression for the velocity function. Now, you know that the derivative of a sine function is a cosine function, and this will be therefore the derivative of sine omega t plus delta will be cos omega t plus delta. Look at this quantity. Now, you must understand that derivative of, now listen to me carefully, derivative of a sine quantity is cosine of the same quantity, and you got to now multiply that with the derivative of this quantity. What is the derivative of omega t plus delta with respect to t? T is the variable there. Omega and delta are constants. So what is the derivative of omega t plus delta? It's omega. So the derivative of this function will be omega times cos omega t plus delta. I hope you understand that. Alright, this is the position function, which is a sine function. Y of t is a sine omega t plus delta. Velocity is the derivative of the position function. Alright, therefore v of t is y prime t, which is a omega cos omega t plus delta. One more time, the derivative of a sine quantity is a cosine same quantity multiplied by the derivative of that quantity. The derivative of omega t plus delta is omega. So a is there, a omega cos omega t plus delta gives you the equation for the velocity of oscillation. Tell me, where is the velocity maximum? The velocity is maximum at the equilibrium position, and velocity is zero at the two extremes. Is that right? Yes. Alright, so if I now draw the graph of the velocity, velocity is a cosine function. Look at the cosine graph. This is the velocity function, v of t equal to a omega cos omega t plus delta. What about the acceleration? Acceleration is the derivative of the velocity function. If this is the velocity function, what is the acceleration? Can you find the derivative of this? The derivative of a cosine quantity is negative of sine of the same quantity, and of course you need to then multiply with the derivative of this quantity. Derivative of this quantity is omega. So, and one more omega will get multiplied here. It will become negative because the derivative of cosine is negative sine. So what is the derivative of this quantity? It will be negative a omega squared sine omega t plus delta. So acceleration is negative a omega squared sine omega t plus delta. Now, can you tell me, where is the acceleration maximum? As the oscillation continues, where is the acceleration maximum? I want to bring this back over here. Now watch here. When I pull it down, you notice that the force is maximum on the mass now. Now, when the force is maximum, acceleration will also be maximum. The maximum acceleration occurs at the lower extreme and the upper extreme. When the object is at the upper extreme, the spring is completely compressed. That means the force is maximum now. So, when do the acceleration become maximum? Acceleration become maximum when the displacements are maximum, or at the two extremes. What is the acceleration at the equilibrium position? At the equilibrium position, there is no net force on the mass. There will be no acceleration. Now, you must be able to explain these in a sufficiently satisfactory way. So how does the acceleration of oscillation change? The acceleration will be zero at the equilibrium. The acceleration will be maximum at the upper extreme and maximum at the lower extreme. That means as the spring gets stretched, the force increases, the acceleration also increases. The acceleration reaches a maximum when the stretch is maximum. Also when the compression is maximum at the two extremes, where the forces are maximum. Alright, let's move on. So the acceleration is negative sine function. Look at that. This is a positive sine function, the displacement or the position function. Acceleration is a negative sine function. A of t is negative a omega squared sine omega t plus delta. I want you to concentrate on this equation for a while. Are you listening to me? Look at the position function. A sine omega t plus delta is the displacement equation. So if you come down here, watch this. A sine omega t plus delta. I'm going to remove this quantity and replace it by y, because y is a sine omega t plus delta. But because a sine omega t plus delta equal to y, we can now write the equation for acceleration as a equal to negative omega squared y. A very important equation. A equal to negative omega squared y. Don't you ever forget this equation. The acceleration of an oscillation. The acceleration of an oscillation is negative omega squared y, where omega is the angular frequency and y is the displacement. Now look at again. Acceleration becomes maximum when y is maximum. That means at the lower extreme and at the upper extreme. Okay. A equal to negative omega squared y. This suggests that acceleration of the oscillating object is directly proportional to the displacement. Is that right? Acceleration varies directly as the displacement because omega is a constant. So this equation suggests that acceleration of the oscillating object is directly proportional to the displacement and is directed opposite to it. That means, what is the direction of the acceleration? As y increases, acceleration increases. But as y increases upward, the acceleration is downward. As y increases downward, the acceleration is upward. The direction of acceleration is always opposite to the direction of displacement. That is what this negative sign says. So watch the sentence again. Acceleration of the oscillating object is directly proportional to the displacement and is directed opposite to the displacement. Now, such a periodic motion. What is a periodic motion? A periodic motion is a type of motion that repeats itself in regular intervals, such as the oscillations of a loaded spring. A periodic motion where the acceleration is proportional to displacement and is directed opposite to it is called a simple harmonic motion. So the oscillations of a loaded spring is a simple harmonic motion. And the acceleration of a simple harmonic motion is given by this equation. A equal to negative omega squared y. So you must be very familiar with simple harmonic motion. And all our discussions on oscillations will be on simple harmonic motion, or SHM. Alright, We will now talk about period